Thank you for the introduction. I would like to present our program DC-PIT, intended for the analysis and design of foundation pit walls. DC-PIT is one program in this large program group DC Foundation, which covers several methods and kinds of geotechnical analysis. And DC-PIT supports different kinds of foundation pit walls. We have bore pile walls, sheet pile walls, diaphragm walls, girder plank walls, and mixed in place walls. And if we enter a new project, you see here a section with the coordinates shown here at the top. And in all the programs of this program groups, you have the most important functions at the left side over these icons here. If we go to an icon, we have a short explanation. And here we have the basic parameters, for example, where is the groundwater level, which kind of earth pressure do we want to apply, active earth pressure, increased active, or earth pressure at rest, and some other basic parameters. Quite important is the selection of the analysis standard. And here we have some, still supporting some older standards. We have the Switzerland SAIA standard, and of course we have Eurocode 7, where we have a number of countries, of national annexes predefined, which can be selected directly. We have here Germany, Austria, France, Great Britain, Italy, and Spain. And we may as well define free standard definitions, which means if you need the standard for a certain country, you can select the Eurocode 7 settings. And for each kind of verification, for example, for the wall length, for the anchor length, piping, and so on, you can select which design approach to use, where the safety factors have to be applied, and the number of the safety factors, which is required for your special country. Now we want to use Eurocode 7 for Germany. And the same is for the design standards, Eurocode 2 for reinforced concrete, and Eurocode 3 for steel. Now when we finish these basic parameters, we first enter the wall that we want to calculate. So with the second icon, I start at the point of 0, and you see that the wall may be inclined if required. And if I click once, there may be several sections. For example, if there is a girder plank wall on top of a bore pile wall, you might have two sections of the wall calculated together, but designed separately, because on one side we have steel and on the other side we have reinforced concrete. Now we just want to have one section of the wall, so I stop this input function with the right mouse button, and the program asks which type of wall to calculate: bore pile wall, diaphragm wall, sheet piling, girder plank wall, or mixed in place. And what is important, you don't need to enter all the parameters manually. If we use sheet piling, for example, we have a large list of sheet pile profiles of different providers: Arbet, Evras, Hirsch, HP, Larsen, and so on. It's a large list. And if we select a certain type of sheet pile profile, we have all the parameters like inertia moment, resisting moment, weight, and so on, predefined here in this window. Now, if I select this type of wall, the program asks for the first soil layer to use. We need at least one soil layer. We can define arbitrary names and arbitrary values for friction angle, cohesion, unit weight, and so on. And we might as well use this parameter suggestion, where we can predefine certain kinds of soil, which we use again and again. So the same thing, if I select one type of soil, I have the parameters predefined here. friction angle 35 degrees, unit weight 20, and so on. Some parameters are not predefined because there are large variations. We might have a permeability coefficient, and we might have the skin friction and end bearing for transfer of the vertical forces, and as well the skin friction for the fixed length of the anchors. So now we have our wall defined and we have the first soil layer. Now we continue with this icon at the left. The third one is to define anchors. So there should be an anchor installed here at 1 meter depth. And this anchor might have an inclination of 20 degrees, for example, a minimum length, which is not the calculator, but the total length required, 8 meters, for example, and a horizontal spacing of 2 meters. And instead of anchors, we might also use a prop, which is support from the excavated side. And for anchors, we have 3 different methods for the calculation. The basic one, standard case, is that the anchor is a fixed support for the wall. If you like, you may select the anchor to be elastic and define a spring constant. So if there is some force on the anchor, we have some deformation depending on the spring constant. And the third option is to use a pretension force for the anchor, which means that the anchor is a fixed support until its force is less than the pretension force, and it is elastic if the required force is higher than the pretension force. Here we will need we will use the simple type of fixed support, and we have the length of the press sector, the fixed length, the diameter of the grouted body for the fixed length, and a certain length from the anchor, from the wall center to the end of the anchor here at the left side. At this time, we don't have an excavation stage yet, and therefore the anchor is only shown in gray because it is not yet used. This is some control at the end if we used everything in the calculation. Then we have a second anchor layer. This should be the same parameters. And you see here that the icon is still pressed. This means I'm still in input mode. That means when I click somewhere, I create a new anchor. Another option is, or if we end the input by the right mouse button, the icon is not pressed anymore. And then I am in edit mode. That means that every element which is available here can be changed by double click. So I edit this anchor or the soil layer, or I could change the wall type and parameters. Now we can have a slope here in the ground. There might be up to 2 slopes in the supported ground at the right side. We can have more soil layers. For example, some gravel here. And as well the values for the vertical forces. So there might be different soil layers in different depths. We have different types of loads, which means we might have concentrated loads on the wall. It might be a vertical, horizontal force or a bending moment. And we can have distributed loads here on the ground in different load cases. What is named here as a load case is in reality a load case combination. So in the same combination, you might apply a permanent load and a live load. And we have as well special railroad loads, which have a special form of earth pressure to be applied on the wall. So this should be a live load at this time. And if we have a permanent or temporary or accidental situation, we have different safety factors which are predefined by the program automatically. And I need a value for this load, 10 kilonewtons per square meter, and this load still isn't used at this moment. And now the most important point are the excavation stages, which means that if we want to install this anchor, we first have to do some excavation to have the space here free for the installation. So our first excavation should be a little below the coming anchor layer. And here we don't have any support before. So we have to calculate with fixity according to Bloom, which means that the wall is fixed by the length below the excavation stage. So the wall is fixed in the ground, and we don't need another support by an anchor, for example. So therefore, these both anchors are not yet acting, so they are not highlighted in blue. So we have this excavation stage still without anchor. The next stage is a little lower, and here the first anchor is already installed, so we have a support here. And for this reason, we don't need this fixity according to Bloom. We can calculate the wall continuously supported by the passive earth pressure. Instead of applying a ground support with passive earth pressure, we might define modules of stiffness. This is for elastic bedding. Here we may as well predefine values, and these values give an elastic support with many small springs, leading to some deformation when there is the load on the springs. There are quite a number of different pages here. We might calculate with a predefined earth pressure or predefinition of water pressure or passive earth pressure. But by default, the earth pressure is calculated automatically. And we can select different verifications. For example, if we have different water levels, there's automatically checked if hydraulic heave could be a problem. And we can calculate the slope stability together with the program DC slope. But this should be, or mostly is only calculated in the last excavation stage. So with this excavation, this anchor is now acting, it is used, therefore not anymore shown in gray. And we need the final excavation stage here, where number 3, where both anchors are acting. And except if we have fixity according to Bloom, we can calculate the wall with a predefined length or make an iteration to calculate the required wall length. Now in this excavation stage, we want to have the slope stability analysis. And now you see that all the anchors and the loads are used. They're not shown in gray anymore. And I again can stop the input function with the right mouse button. So we have all our excavation stages finished here. There might be a slope in the excavation as well. And then we can calculate this wall, define some file name here. And now we see the iteration of the circles of the slope stability analysis. And we finally have an end result here. And if not every verification is fulfilled, we will have an overview window. And you see here most of the verifications are okay. And only for the boom holding the anchor, we will have to look at later. There should be a larger profile to be used. And I can check what is the problem. We have bending moment and interaction not fulfilled, and we will have to check this with a larger girder at this boom later. Now we have the calculation finished. So we have different types of results. First are the graphics, and here we can define a quite large number of different types of graphics, which are not used always, and therefore we can predefine which graphics we want to have. What graphics do we want to show? And this is done under settings configuration. Here we have all the different graphics available, and we select that we want to see the geometry plot with the required wall length, anchor length, and so on. We want to see the earth and water pressures, and we want to see the section forces as characteristic values without safety factors from total loads. You might select to have the values only for dead loads, only for live loads, only for water pressure, and the design values. But this, most of the time, this is not required. So we have a predefinition here. And these graphics may be selected under this icon. So there's just one thing missing. You see that the water level here is still at 1.50 meters on the excavated side. So for the different excavation stages, we need to have a lowered groundwater. So for an excavation depth of 4 meters, we should have a water level of 4.50 meters, for example. And here we need a water level of 6.50 meters. To have an excavation without water. And from these different levels here, from 1.50 meters to 6.50 meters, we will have some water pressure acting on the wall. So we have to calculate again, having the wall load including water pressure. And then we can look at the result graphics. And here we have the selection. Everything can be selected which was predefined in the configuration. We can select which load case to see, which excavation to see, and can define the scale, which is matching to our defined sheet. And now we see for the first excavation stage, where the wall is fixed here in the ground, we need a total wall length of nearly 3 meters. And now we can switch with page up, page down through the different graphics. And here we see the earth pressure applied. The earth pressure from block loads, limited block loads, is shown separately. There might be a redistribution of earth pressure. At this stage, we still have no water pressure because of the same level at the left and right side. And we have the total load applied on the wall. And from this load, we must look for the wall length where the bending moment is going to a value of 0. Because in reality, there is no fixing at the end of the wall, so there should be no bending moment. What we have at this point is a shear force, a supporting force at the end of the wall. And this is the reason why we have here a calculatory wall length of 2.70 meters, while in the geometry graphics we had nearly 3 meters. So the difference is what we need to support this shear force at the wall end. So this is shown automatically in the graphics for the wall length, which wall length really is required for these loads. Now the same for the second excavation stage. Here we need 6.75 meters of wall length. We see the anchor force with characteristic and design value, and which is already calculated for the horizontal distance of 2 meters. By default, we calculate everything per meter wall. And as we define the distance of the anchors of 2 meters, we can calculate the force per anchor with a 2 meter distance. Here again, we have the loads now with the water pressure from this distance of the two water levels. And the section forces, here there's a support force creating the anchor force, and we have the deformation of the wall. And the same for the third excavation stage, where we have as well the slope stability, the circle shown with a verification which is nearly fulfilled with 102%. And again, we have the loads and we have the section forces. This is the graphics as an overview. And then we have a detailed result output. Here where we can see all the calculations. We have the input values of wall, soil, and loads. We have the safety factors. We have the earth pressure applied. We have the calculation here for the first excavation stage for the required wall length going to a bending moment of nearly 0. Passive earth pressure, water pressure. Here the calculation of the additional depth of 24 centimeters. Here we have the verification of the ground support, that the support force which we calculated is not higher than the design value of the passive earth pressure. And then the load and section forces in the wall. And finally, the verifications of vertical forces, that the vertical component of the passive earth pressure is activated and that all the vertical loads can be transferred to the ground. And these results, mixed with the graphics we have for any excavation stage. We have the verification against hydraulic heave, section forces, and so on. And finally, at the last excavation stage, we have the detailed verification for the required anchor length. So we see that for both anchor levels, we need lengths of 10 meters and 50 or 40 meters and 60 to have, there was one calculation more for total loads. Here we have 40 meters and 60. And we have, again, the graphics for the third excavation stage. Then as the third part, we have the design of the wall, which means we go here to this design option. We calculate the wall itself, the anchors, and the booms. And now you see we had selected this arbet profile PU18, which is quite large and will not be required by the small loads that we had. We have here a maximum utilization of 40% for bending design. Here we have 20%. So we would not need this large steel sheet pile profile. So we could select a smaller one, or we use the function suggestion here. And with this function, the program calculates a complete line of sheet pile profiles and looks for the smallest one which supports all the loads and where the verification is fulfilled. So it is calculating again because we have a different stiffness now for this sheet pile profile. And we see now that an arbet GU7S would be sufficient. And here we have an utilization of 95% for the steel design. So 95 is the highest value, and this is sufficient for the wall. And for anchors, we can select different kinds of anchors. We have cord anchors, multi-bar anchor, single bar anchor, Ishebig Titan, and tie rod anchor. And for our two anchor levels with different forces required, the program tells us which kinds or which numbers of steel bars, for example, are required. For example, for a cord anchor, we would need here 4 cords. For a multi-bar anchor, 5 diameters of 12, or for a single bar anchor, 32 millimeters of diameter. Ishibeki, we could use a type 7353. And so this is verified here with a required safety factor for the anchor steel. And in a second table, we have the verification for the fixed length of the anchor. So in this case, we see that we have a higher value that we had before. From the calculation of the wall, we had a required anchor length of 40 meters and 60. But here we need a longer fixed length. So we have a longer total length required for anchor plus fixed length to transfer these forces from the anchor to the ground. And finally, for the boom, we see that here not all verifications are fulfilled with a type 2 times U100. So we can again use the suggestion, and we see that we need a type U140 for the verifications to be fulfilled. And the same for the second anchor layer. Here we select suggestion and need 2 times U240. So far for the different types of verification for the design of the wall. And just a short look to different types of walls. We had a sheet pile wall first. And now, for example, if we want to use a bore pile wall, we can define the diameter of the piles and the spacing, which means if this value is more than 0, we have a spaced wall. If it is 0, we have a contiguous wall. And if it is negative, we have an overlapped bore pile wall. So, for example, 10 centimeters overlap. And if we calculate this wall, then we have a different kind of design because we don't have a steel wall, but we have a reinforced concrete wall. And we can see this if we go to the design. And you see, for example, if we have 3 non-reinforced bore piles between 2 reinforced piles, we have here the force in the non-reinforced section, and you may select how many non-reinforced piles we have. For example, all the section forces are calculated per meter wall and then multiplied by the distance between the reinforced piles, giving the section forces per pile, which may be used or which must be used for the design of the pile. And we could then select, for example, if we have diameters of 28, we need 8 bars in the pile for these section forces. If we have a pile arrangement only 1, 1, 1, and we calculate again, which means we have only 1 non-reinforced pile. So the force in the non-reinforced concrete is different. We only have a pile distance of 1 meter and 8. And therefore we have smaller section forces. And for example, with diameter 28, we only need 4 steel bars. So we could, for example, use diameters of 16, where we have 9 bars required. After this verification of the critical section forces, we have the shear design for the pile, and then we have the design in different depth sections where we see where we need a higher value of reinforcement or a smaller value. So the highest amount of reinforcement is required here in about 6 meter depth. And until about 2 meters and 50, there are only small values. So we could, for example, select until depth of 2 meters and 50. If we select diameter 16, we only need 4 bars instead of 9. And this reinforcement may also defined in different steps here on this page. And we see that, for example, if we define the reinforcement to 2 meters and 50, we need 4 diameters of 16. Then until 7 meters and 50, for example, we need 9 bars. And until the end of the wall, we need 5 bars of diameter 16. So we have these steps in the design which can be selected and which can be used for the creation of the reinforcement for the ball pile wall. Now finally, if we use a girder plank wall, for example, we can as well define the different types of these girders. We have the U types, HEA, HEB, HEM, IPE, and so on, different types. And if we calculate this wall again, we have a different type of dimensioning. We have again steel profiles, but in addition, we have infilling between the profiles. So this is again shown in the design. And here we may select a timber infilling or concrete infilling or a steel plate. So this type of material can be selected. We can select different materials, for example, a timber grade of C16. And then this is dimensioned. So we have with 4 centimeters thickness, we have our stress verification fulfilled. And the same for shear and for the bearing pressure, which is here the support of the timber infilling to these steel members.